All right, so last time we developed a weak form and then we put it in this bilinear form where we had terms that involved del u and u and terms that only involved del u. And we called this the variational problem. And then also we use that to infer a quadratic functional. That looked like this, and I said that solving the variational problem, solving the first equation, is equivalent to minimizing the quadratic functional I, right? And when we actually, so strictly when we use an approach that minimizes the quadratic functional, what we're doing is strictly called Ritz method, and then we're going to work an example today, okay? And then I mentioned that the finite element method is just a piecewise extension or a piecewise implementation of the Ritz method. But in the finite element method, we don't really minimize the quadratic functional. We rather solve the first equation, okay? But I want to give you an example of just using Ritz method one time so that you can kind of see where the mathematical roots of the finite element method come from. And there's some history here that sort of makes this significant because when the finite element method was first invented in the late 60s, it was very, very dismissed by the mechanics community at large or the mathematics community because, again, it was sort of introduced as this matrix method in structural mechanics, and that then when you extend it to, say, finite elements over continua, it wasn't well accepted, and it was very, very much dismissed. But then once the mathematicians sort of got a hold of it and realized that it's just a piecewise implementation of the Ritz method, which has been well accepted and established for more than 100 years, then it sort of led to some acceptance of the method, which, of course, now, I mean, it's sort of hard to believe that the finite element method ever was met with any kind of dismay because it's sort of the way we do engineering at this point. I mean, it's ubiquitous. Okay. So, in the Ritz method, we're going to use the weak form, or more specifically, the quadratic functional we infer from the weak form. And this has the advantage that the approximating functions those are the the interpolants. I think maybe last time I used phi. They only need to satisfy the essential boundary conditions since the natural boundary conditions are included, right? They're already in the weak form. So we seek an approximate solution, UH, that's of the form and that's probably the sixth time I've written that, right? So the CJs are unknown coefficients, and the phi j, or the phi j's are interpolating functions of x in 1D. And what we do is when we plug in this approximated function into our quadratic functional, right? So when we plug in u of h into the quadratic functional, our functional becomes a function, right? So remember that b and l, well, they have integrals in them, right? So it's a functional, it's a function of function. But then once I plug in this approximation, I can then compute those integrals, right? These are just unknown constants. So I can just pull those out and compute the integrals then. Okay? And now I just have a function of unknown constants. After I compute the integrals, I just have a function of unknown constants. And once I have that, then I can just use the method. So, substitute in u of h, integrate. Now I have just a function of x, right? And c, right? I'm sorry, not even a function of x. Then I just have a function of the unknown constants. And then I can just use the methods from ordinary calculus to determine where there's a minimum, right? So then I just take the partial derivative with respect to each Cj, set that equal to 0, and that gives me the J equations that I can then solve for the unknown C's. So here's an example. So here's an equation that's going to be over the domain from x equals 0 to 1 with the initial u at 0 equal to 0 and u at 1 equal to 0. So two essential boundary conditions. All right. Now we can develop the weak form for that. There's a three-step process. I won't do it. I'm just going to write down the weak form, but let's remember what the 3 steps are. Step 1. Multiply by a weight, move everything to one side of the equation and multiply by a weight function. Step 2.
Integrate over the domain.
And integrate over the body and integrate by parts to shift some of the differentiation off onto the test function, right? And then step 3, compound the boundary conditions. That's it. So if we do that, the weak form is that, and I've written it in such a way that I've grouped the terms that involve del u and u and the terms that only involve del u. Right? So with that, my quadratic functional becomes that. All right. So then I'm going to substitute in my approximate solution, and I'm going to use C1 times x 1 minus x plus C2 x squared 1 minus x plus C3 x cubed 1 minus x. All right. Remember last time we said that these have to be linearly independent, right? So it's clearly are. This multiplied by x and multiplied by x. So they are linearly independent, all right? So then I have just the three unknowns. Once I substitute my approximating function, substitute this into that, and integrate, and I just have the only unknowns are the c's, and then I can just use the techniques from ordinary calculus. So I just have an equation like this, another one like that, and another one like that. All right, so let's do it. I'm gonna do it in Mathematica. So I have u of x equal, can you guys see that? Can you make it a little small? Is that okay? Okay. So, so u of x is c1 x 1 minus x plus c2 x squared 1 minus x plus c3 x cubed minus x. Okay, so then my quadratic functional is 1/2 the integral from 0 to 1 u prime x, so that's the first derivative of u with respect to x, squared minus u squared plus 2x squared u of x dx. All right, and this is one reason I like to use Mathematica in class, because you don't have to understand the syntax. I can make an integral and it looks just like an integral, right? So you don't have to understand some cryptic syntax if I was using some other language, right? Okay, what happened? There we go. That should work. Okay, so Mathematica performed the integration for me, so now you see it's just a function of the c's, right? So then I can make three equations. Equation 1 is equal to d I c1, and that's equal to 0. So there's one equation. So taking the derivative with respect to so now I have my three equations. And you see these are just linear in the unknowns now. So I can set up a linear system, solve that guy. So solve equation 1, equation 2, equation 3 for the unknowns. So there's my solution. So then I can plot that. So there's my approximate solution to the differential equation. All right. So that's an example of using Ritz method. Both last time when I used this sort of generic weighted integrals method, which turned out to be, if you really want to classify it, a Petrov-Galerkin method. And this time when I used Ritz method, I didn't give you any clue of how we choose these interpolating functions, other than I just said what the requirements are. I mean, they have to be linearly independent. They have to satisfy the essential boundary conditions, right? But that still gives you a lot of freedom and choice of how you choose them. And sometimes that's a good thing. You can use some knowledge that you may have about the solution to pick something that works well. But it's very difficult to do in general. So what we really want is more systematic way. Right? And so let's talk about some more requirements on the interpolating functions. So how do we choose them? So again, so otherwise, that's the things we've talked about. So otherwise, the phi j have to satisfy the following. They must be selected such that when you plug them into the bilinear form, it's defined and non-zero. In other words, they have to have the proper continuity requirement. So if I have if my bilinear form has some term that has partial derivative of u with respect to x, the second partial derivative of u with respect to x, and I choose my approximating function to be x, well, when I take two derivatives of it, that's going to be 0. So it has to be non-zero when you plug it into the bilinear form. They must satisfy the homogeneous form of the specified boundary conditions. So that is, if you're given u at 0 equals to some u naught, phi j must satisfy u0 equal to 0. Okay? The other thing we've already talked about, right? The set of phi j must be linear independent. Right. So there we chose phi 1 equal to x 1 minus x, and phi 2 is equal to x squared 1 plus x. Those are clearly linear independent, right? There's nothing I can add to this to get this. Right? But, or I mean, there's no constant. There's no constant I can multiply by that to get that. So in other words, if I would have chosen phi 3 to be equal to 2x squared 1 minus x, this would not be allowed, right? This is invalid. The set phi j's must be complete. So in other words, if I have a set x, x squared, x cubed, x fourth, this is complete. In 2D, or if in x and y, if I have x, y, xy, x squared y, x y squared, x squared y squared, this is complete. However, if I have x cubed, x to the 5th, x to the 25th, it's not complete. Likewise, x, x squared, x, y cubed, not complete. So in other words, a complete polynomial is one when it actually comes from Pascal's triangle. Does anybody know what Pascal's triangle is? So you have like 1, xy, xy, x squared, y squared, and so on, right? X cubed, x squared, y, y squared, x, y cubed, and so on. So that would be Pascal's triangle. So whenever you use this to construct them, you basically, you'd take like this, or you'd take like this. Yeah, it's complete. You can also, as long as you take a symmetric, you could do like this. If you had some kind of funny 5-noted, 4-noted, yeah. So no, that's not the funny case. Actually, that's the normal quad in 2D. A quad in 2D. We haven't really talked about nodes and finite elements yet, but the quad in 2D would have 4 nodes, so you need 4 approximation functions. So you'd take 1, xy, xy. All right, so the last thing is that, yeah. the phi 0 term must be the lowest order function that satisfies the boundary conditions. And here we almost always use polynomials. So whenever someone talks about the standard finite element method, you know, if they don't give you any more information, or in fact, if they just say the finite element method, you're talking about linear approximation functions, or you know, polynomial approximation functions, but usually just linears. So just linear interpolants. So so let's try to use a polynomial, or construct a set of polynomial bases on our same example, right? So that, just to write it down again, and quadratic functional is that guy, right? So we want U, it's approximately U of H, Cj, Pj. And we're going to use a polynomial, so we're just going to say C1 plus C2x plus C3x squared. Now we have to make this thing satisfy the boundary conditions, right? So U at 0, if I plug in 0 into this equation, that implies that C1 equals 0, right? So if U1 equals 0, if U at 0 equals 0, and I plug that into the approximation function, that implies C1 equals 0. So 0 there, 0 there, those terms go away. So C1 equals 0. Okay? U at 1 equals 0 implies, so C1 is already equal to 0, so I'm going to just say that's 0. Then I'm putting 1 right there. So 1 and 1, so that's C2 plus C3 equals 0. Or C2 is equal to minus C3, right? So when I plug that back in, my U of H becomes minus C3x plus C3x squared, or if I factor it, then I have this guy. All right, so let's, using that approximation, let's look at this again, okay? So I'm just going to copy everything down here and put in, so C3 is x squared minus x. So then when I compute the integral, I just have a function of C3 now. Right? So now I just have one equation I need to solve. Compute the derivative with respect to C3 and solve that guy for C3. And then plot the solution. So it's clearly different than that, right? I use a different approximation, so, okay. So which one do you think is right? Well, they're both approximations, right? Turns out this differential equation we can solve, right? So it's, let's see, if we go d-solve minus d u of x with respect to x squared minus u x plus x squared equal to 0, u 0 equal to 0, u 1 equal to 0, x u x. Oh, I better use some, not a u, because I defined u up above, so it's, I better use v. So that's the exact solution, and we can plot that. So that's the exact solution to that differential equation, and that's the plot of it. Right? So in the first example, where I just sort of arbitrarily pulled those guys out of my hat, it turns out I had some knowledge of the exact solution, so they were pulled out of the hat in such a way that they'd give me a better approximation of the exact solution. Right? But usually, we don't know the exact solution. That's why we're using the finite element method. Right? We're trying to come up with an approximate solution, and so we need a more systematic way of going about it, and thereby we'd use polynomials. Now, we could do something to help our approximation with polynomials. What would that be?
Subdivide the domain, or add more.
Yeah, either one. Yeah. So subdividing the domain would require introducing elements, which we haven't got to yet. So for let's say we don't have that choice in our arsenal because we don't know what elements are yet.
Increase the order of the approximation.
Increase the order of the polynomial approximation. So if we increase the order of the approximation, then we have more coefficients. You know, the system would get larger, and then we could become a better approximation. So I didn't really plan to do that, and I don't have it in my notes, but you want to try it? Let's see if we can do it. See what happens if we increase the approximation order. So all right, so let's just go back to a generic form. Say C1 plus C2x plus C3 x squared plus C4 x cubed. Okay. Now we have to make it satisfy the boundary condition. So u at 0 must equal 0. And we'll solve this for C1. I'm just doing it all programmatically. I know that's pretty obvious, but the reason is I want to make a substitution here. Okay. So then if I say u at 1 must equal 0, and I want to substitute in the solution, the first solution, and solve for C2. Okay, so now I have that. Okay, so then I'm going to say well, I'll just say u, well, what can I do? U x equal to u at x slash dot sol 1 slash dot sol 2 . Well, let's do V or W. Okay, so there, I'm just testing out my function. I solve for the coefficients that satisfy the boundary conditions, and then I just plug those back into the original U1. I don't even have to do that. That's making it too confusing, actually. Let me, I can just do it in the quadratic functional. All right, so I just assume the polynomial, solve for the coefficients that satisfy the boundary conditions, and I'm just going to substitute those in to this guy. Okay. All right. All right, so then I have that, which has two unknown coefficients now, C3 and C4. So I have two equations. So then I can solve those two equations. What's going on here?
Oh, C1 and C2 are in terms of C3 and C4.
There we go. Oh, a little better, right? And of course, I can go on increasing. The order of the interpolation until eventually match exactly, but it's pretty close even with just a third order polynomial. Okay, I finished a little fast today. That's all I had. Is there any questions? So next time, and I'll probably assign a homework later today. So look for a note or an email. So next time we'll officially be doing final analysis. So the thing that the next step is to introduce a discretization. So introduce nodes, right? So how do we break? In 1D, it's easy, right? We just take our one-dimensional line segment and break it up into smaller line segments. In 2D, we break it up into triangles or cubes or quads.
Would it be easier to use mathematical code like mathematical?
Use whatever you want to use on your homework. Yeah. So again, the only reason I use Mathematica in class is because when I write an integral, it looks like an integral. And you don't have to ask me what the syntax is, right? I mean, everyone can understand that. It looks like I'm writing math on my paper. That's the only reason I use it. You can use whatever you want. Okay?